Hello, everyone. This is Group 5 from EAI 6010 and Northeastern University. And today we're going to talk about image classification. My name is E.
My name is Henry.
My name is Kinshuk Singh.
My name is Priya.
All right, so in the beginning, I want to talk about the purpose of the project. So the goal of this project is to build a baseline convolutional neural network model for image classification. And the data set that we have, it's 10, it's the animal data set, animal images, 10 categories. And the goal is to recognize and categorize the different animals using the model. Uh, uh, the reason why we picked the CNN model, it's because it's a good model. In the feature extraction and pattern recognition from raw image data. And this doesn't have to be a recognition of animals only. This model and what we did can also be used in other field, medical field, education, pet apps. And this just a demo and um, in the very minimum what we can do for this. And I'm going to talk about the dataset overview. So we have 10 animal classes, around 24K images. And the images are cross-checked by 5 separate people to make sure that's the right image for the right animal. So we got dog, spider, horse, squirrels, etc. And the dog and spider has the most image in the data set, which will increase the recognition accuracy a lot.
Okay, in the slide 4, we have the environment setup. So one of the most biggest hurdle in AI project is just getting everything to work. So especially when people are using different machines or operating system or even the setups. So we have all heard that like phrase called it works on my machine, right? So to avoid this, we built a clean, consigned environment using Anaconda and Python 3.10. So this made it easy to install everything we needed and ensure we were all working with the same tools. So we created a dedicated environment just for this project, added GPU compatibility for PyTorch and even run a quick test to make sure our GPU was being used. Then we installed a few essential libraries like datasets, uh, Matplotlib and JupyterLab, which helped us with everything from data pre-processing to training and visualizations. So the best part, once it's set up, anyone can run this project wherever you are using either a local machine or a cloud GPU and get the same result. So no more setup headaches. So next slide, please. Okay. Over here, we are talking about model architecture. Our model is based on a classic CNN. It's like one of the go-to architecture for image classification and for good reason also. So here is how it works. First, the convolutional layer scan the image and pick out key features like edges, shapes, and textures. Just think of it like how our eyes might notice patterns like fur or feathers. Then we can apply batch normalization and ReLU activations functions, so which basically helps the model learn faster and avoid getting stuck during training. So we also use max pooling, which is kind of like zooming out and keeping only the most important details. So this reduces the amount of data the model has to process, which makes everything more efficient. So finally, all of these learned features are passed into a fully connected layer that makes the final decision, predicting which of the 10 animals it thinks is in the image. And even though it's a relevantly simple model compared to the advanced one like ResNet, it's actually performed really well on this data. So, yeah, that's it.
So this slide represents a lined graph titled Accuracy versus EPCOs, comparing train accuracies and validation accuracy over 5 training EPCOs. The x-axis represents the number of EPCOs, that's 1 to 5, and the y-axis shows accuracy ranging from 0 0.4 to 1.0. The orange line represents train accuracy, and the yellow line shows the validation accuracy. So the key insights I want to address is like the both train and validation accuracy improve consistently over EPCOs. The train accuracy starts at 0.50 and increases to about 0.96, and validation accuracy starts to like 0.39 and rises nearly to 0.95. The gap between the two narrows over time, suggesting this model is learning well and not overfitting significantly with these 5 EPCOs. This slide effectively demonstrates strong and steady model performance improvement. Can we go to the next slide, please? Yeah, so this is a slide 6 that says confusion matrix insights. Here's where we evaluate the model's prediction using a confusion matrix. We achieved an overall validation accuracy of approximately 95.6%, which is quite strong for a dataset of this size. Notable, the model performed extremely well in identifying dogs and spider images, showing high precision and recall for those classes. However, we noticed misclassifications between cats and squirrels, which could be attributed to similar color palettes or poses in the image. This kind of error analysis is critical because it helps us understand model weaknesses and consider targeted data augmentation architectural changes in future iterations. That's all.
So, hello everyone. I'm gonna to briefly walk you through our web deployment process. We choose Gradle for our base web framework. We created a requirements text file listing our dependencies. Uh, uh, they are Gradle, Torch Vision datasets. And next we wrote app py file, which does 4 key things. First is to load the model weights into the ResNet 18 classifier, and we define and then define the image processing pipeline to resize and center crop and normalize into the tensor. And we implement a predicted image function that returns both predicted label and its confidence score. And at last, we wrap the function into Gradle interface. So as we push those files into GitHub and created a Hugging Face space using the template, the platform will automatically install our dependencies and build the app. And it will issue a permanent URL. So anyone can open the link to upload the image and instantly see our model's prediction. Next slide. So on this slide, you see our live demo hosted on the Hugging Face space. So users can simply drag to upload the photo, and it will immediately return the result as dog and 74% of accuracy. And as for the spider picture, it will return as 99% of accuracy.
Thank you. And now I'll talk about pro and cons and give a little conclusion of the project. So for the pros. This is obviously a really good model for image recognition. Learning its own features was the convolution layers automatically pick up visual cues like textures or shapes, and it and in the earlier my as what my teammate was talking about, the accuracy was even above 95% when it comes to the 10 animals. Uh, and when it comes to like the computing power, it's only gonna take a small edge GPU or your mobile MPU. Um, and the cons are first I want to talk about it's going to be very costly training when it comes to hardware, especially this just simple demonstration. But if you want to upgrade this to the enterprise level, industrial level, it's going to be it will require more hardware and computing powers. And the computing power is obviously going to cost money. The cloud computing, stuff like that. The hardware, you have to either also have a cloud storage that was going to cost money, or you have your own storage data center, which is also going to be very costly out of like what we can do right now. And also when it comes to the data set, collecting additional image can be very difficult, especially in different area, different country. There the rules that comes to collecting images can be very strict, and the licenses are very different. And also labeling those images can also take a lot of time and uh, manpower, basically. But I still think this is a meaningful project and it has this potential for future extension. And this is the reference. Thank you for listening. Bye.
So how much time we use?